All right. Welcome back. Fourth lecture in Inf 4820. My last lecture for this first part of the course. Starting this coming week, Mohaf will take over. And today we'll have fun. We'll wrap up our introduction to Common Lisp and then use at least half an hour on a quiz. And there are even bonus points available. 75 of you submitted for our first obligatory assignment earlier this week. Well, yesterday. Thank you very much. Elena is now grading. She decided she could do all 75. We're hoping that most of you will have feedback already this coming week. Certainly before the next submission deadline, which is actually 2 weeks from now. Part A of the second obligatory assignment was published yesterday, and it's something that you may well start to work on already. A few of you at least were surprised that in our first assignment we seemingly asked you to use pieces of Lisp that we hadn't introduced in the lectures. Hash tables, data structures, and functions, and we're going to do that again. It's part of our program. It's called immersion teaching. We throw you out into the deep end of the pool, and then most of you will learn to swim. Well, that's maybe not the right metaphor. It's called immersion teaching. Everyone will be a perfect swimmer. But please, those readings that we post on the course page, we mean it. So the answers to everything you need to know are available, but we are not spoon-feeding you every one of them in the lectures. There's not enough lecture time to do that. All right. Was that enough of a moral appeal, Mohaf? Mohaf will take over next week. You can have your own moral appeal then. All right. So higher order functions and flexibility of argument lists and the mighty loop were our core topics last week. Today, 2 more slides on loop, because there are so many things it can do. We'll never do justice to it. And then putting in a few more reflections on things you've used already, and introducing briefly facility to define abstract data types. And then most of the second half of today's meeting for the quiz. So this is a 1-slide high-level summary of most or many of the loop constructs that I find myself use frequently. There are more. Loop is a designer extension language in Lisp. It's implemented in Lisp through the macro facility for all sorts of iteration. For example, I can iterate over the elements of lists or vectors using for, some variable name symbol in, on, or across. List or vector, this should be. I can count for, variable name, optional from, optional to, down to, by number. In fact, I can count from 1 without a 2, and then it will count indefinitely. I can iterate over hash tables, for variable being each hash key or hash value in a hash table. I can have local variables that I compute using arbitrary expressions in each iteration step. For variable equals something. The S expression is evaluated. Its value will become the current value of symbol in the current iteration step. That's the initialization first step. All subsequent steps will use the then clause. It's optional, so if there's no then it will always use the equal. Important, often I iterate to compute some value. Sometimes I iterate just for side effects to print something out. But whenever I want the loop to return something, then I need an accumulator. I need to collect or append or sum or minimize or count. There are many ways of accumulating results from the iterations. In addition to these, for x in or from to, I can also control execution more explicitly. I can say while, until, repeat some number of times, when, unless, and so on. I can give myself local variables with symbol equals something. That would be equivalent to wrapping the loop inside a let. So it saves some indentation. I can have dedicated as expressions that I evaluated before the iteration starts and after the iteration has terminated. And all of these can be combined freely. That is, I can at the same time iterate through a list and count in a range, and also do the sort of stepwise computation here using arbitrary expressions. So there's really very broad limits, if there are any limits, to what you can do in terms of iteration using loop. That does not mean that you should stop using recursion. There are problems, and we will encounter problems that are very naturally approached in recursion. For example, traversing a graph. Clumsy to do in iteration, very natural to do in recursion. Without at least one accumulator, loop will only return nil by default. So if I don't accumulate explicitly, if I don't collect something or sum something, it will actually only return the default value nil. Few more examples. For foo in 1, 2, 3, collect foo. That's something you've used already. That just gives me a list where the value for the iterator variable foo in each iteration is collected in one list. A variant of that for foo on 1, 2, 3, collect foo, probably not something you've used. The difference is that the in iterates over the cars, the firsts, the elements. The on iterates over the cuddas, the rests, the remainder lists. So here, the first iteration step, foo on a list is the list at large. Second step, it's the list minus the first element. Last step, it's the list minus the first two elements. So the empty list will terminate this loop for foo for x on. These are complementary. One iterates over the firsts, the other iterates over the rests. I can also change how I accumulate. Collect essentially means at each step there is a value and I join them together using the list function. I build a new list that contains all of these values. I can accumulate using append. So here I have 3 lists, the 3 successive remainders. If I say append foo rather than collect foo, then these are appended into one flat list. So it's the result of apply #quote append on this thing here. And my final example, that's sort of doing counting in a range, conditional accumulation. So I can say when I is even, then collect it into a local variable, evens, else collect it into odds. So I split the numbers between 2 and 10 into 2 lists, the even and the odd numbers. And finally, I return a new list that contains these 2 splits, and that's the result I'm getting. Okay, so that was my last slide on loop, and unless there are immediate questions, I'd propose I move on. Loop, in my view, is a good example of the Lisp philosophy. When you do something, do it right. Do it systematic, comprehensive, allow all of the generality that a programmer might want. The same, I would say, goes for the argument list flexibility. The optional, the named, the rest parameters, all of that. This is something you've used already. Input and output, like in all programming languages, is mediated through streams. T is overloaded. So far we knew it, the symbol T, that is self-evaluating as a truth value for true. But we can also use it as a shorthand notation to name the terminal stream. So format takes a stream argument and prints something to that stream, in this case the terminal. And here we use 2 different arrows to really highlight the distinction between some printed output, that's a side effect, to the terminal or to a stream, and the return value. This is what determines the semantics of this expression. And format is an expression that we exclusively used for the side effect, like def parameter or defun, and hence it has no interesting return value, it returns nil. But that's a very important distinction that you need to be clear about. Printing something to the terminal is not the same thing as returning it. Only what is returned will be visible to a consumer of that expression. So if I make that expression an argument of another expression, only the return value will be accessible. And input, I can do read line, line-wise reading, or read as expression-based. That's often going to be useful. I give both of them a stream argument, and I can give them an optional additional argument, nil, and the second reader argument is what will be returned when we reach the end of file. So for read, that will, from stream, obtain the next well-formed as expressions. That could be just a number, that could be just a symbol, that could be a double-quoted string, it could be a list. It could be any well-formed Lisp as expressions. When we reach the end of the stream, the end of file, then we will return this second argument here. Does anyone foresee a potential problem? And so I read, that's in fact what the compiler does. It reads when you ask it to evaluate or compile an entire file. It reads it one as expression at a time. So I go through a file and read all of the as expressions that it contains. It's maybe too subtle. Of course, nil is a valid as expression. So nil actually is not a very good value here to use as the end of file marker. I should ideally find something that cannot occur among the valid as expressions in an arbitrary file. The compiler, of course, typically reads defuns and def parameters, but I'm pretty sure the compiler actually has, instead of nil here, some symbol that only the compiler knows about, and that symbol will be how it knows that the reader has reached the end of file. And something that Lisp had very early, I was going to say pioneered, but I'm not entirely sure of that, that is now becoming increasingly common, is to actually wrap the opening and closing of files into block statements, block expressions as it were in Lisp, because all we have are expressions. So with open file means connect the local variable stream to the contents of this file for reading. That's what we say here. And then in the body of the with open file, stream is an open stream. And when I leave this as expression, the with open file expression, the stream will be automatically closed. So no explicit open and close as is traditional in many programming languages, because that brings the risk of forgetting to close. And not closing streams is not good practice, and there are often operating system limits on how many streams you can have open at the same time. There may be an exception. So if an exception throws us out of the scope of the with open file, the stream will be closed. Don't need to think about that. That's the proper way of doing this. And becoming more and more common in modern programming languages. Any questions? I'm rushing through a shopping bag of sort of all of the pieces we haven't reflected on so far. So, arrays, I think we did not use in the first assignment. Arrays are just arrays. They're integer indexed containers where the indices naturally start from 0. Position 1 is at index 0. We're computer scientists. Make array is the constructor. Arrays print like this, a hash mark, and then something that looks like a list, but it's not a list. It's an array. It's a continuous block of memory where the positions are indexed by integers. Aref, array reference, takes an array object and indices, one index or more, and it's suitable to retrieve a value at that position or assign a new value. So I can combine it with setf. It's what we call the generalized variable. It's something that can be assigned to. And now, if I evaluate array here, then in the first position there is a new value. The The default arrays in Lisp are fixed size, but there is support for adjustable arrays where I actually resize them when I run out of space. But that is a costly operation. So I would only use that when you actually need it. Resizing an array may mean copying all of it to a new memory location because it has to be a continuous block of memory. They can be multidimensional, they can be grids. And here I just give make array a list of dimensions, in this case 2. So I want a 2 by 5 array, total of 10 cells in two dimensions. And there is an optional keyword argument here where I can specify what I want to be the initial value in the new array. And so this prints like this, but it really corresponds to this block of memory. And again, I can use aref now with 2 indices. I need as many indices as the array has dimensions, obviously. And write to the contents of one cell. All very straightforward, isn't it? Then, something slightly more interesting and useful. There's a generalization over a subtype of arrays, namely the one-dimensional arrays, which are often called vectors, and another subtype of vectors, the strings, that is vectors that contain characters. And similarly, there are also vectors of bits, bit vectors, and all of these are organized in a type hierarchy, a hierarchy of data types. And there's an abstraction for vectors, that is one-dimensional arrays, including strings, and lists, and that abstraction is called a sequence. A list, as we learned, is this chain of cons cells. So it can have arbitrary size, it can grow or shrink as we see fit. I just add more cons cells or take some out. It's what is called a singly linked list in data type terms. A vector is a one-dimensional array. It's a contiguous fixed size block of memory. It's indexed by integers. So, but there are many operations that operate over either vectors or lists. For example, length I can do of a string or of a list. Counts the number of elements. ELT, element. We've seen nth before. That's specialized for lists. Gives us the element at index I. ELT generalizes that to vectors or lists, that is sequences. So I can do ELT foo at position 0, or I could do ELT list 1, 2, 3 at position 0, and it would give me the first element. And now here many more. Countif counts, so it takes a predicate, it's a higher order function, counts how many elements of this sequence, which could be a string, satisfy this predicate. In this case, there are 2 numbers. Subsequence, given a sequence, a string or a list or a vector, gives us a new sequence between these index positions. So starting from index 3 and ending before index 6 is how that counts. Substitute. Here I'm substituting the character A for the character O in the string ho ho, and that makes it ha ha. Remove. So I'm alternating here between different types of sequences, strings and lists, but in all cases, in all of these examples, I could swap that around. Sum is a predicate that takes another predicate and will return true if this predicate is true for at least one of the elements in the sequence. So there is one list here, and hence sum gives us true. There's a parallel predicate called every, and every hash quote list p of this list would be uncomfortable silence. No. So I was counting on you to sort of get what every probably would do based on the parallelism to sum. So every like sum is a higher order predicate, and it will test whether all of the elements in the sequence satisfy this predicate. So in this case, are all of them lists? No. So one is, hence sum returns true, every would return false. So if I want to test all elements of some list for some property, I can say every predicate that defines the property for one element. So all of these are applications of, or many of these are applications of higher order functions. Sorting is another one. I can sort sequences, strings, or lists using the same sort function. And of course, I give it a predicate that needs to take two arguments and provides a partial order to use in sorting. So hash quote less than is the numerical ascending order predicate, and hence I get back this list in sorted increasing value order. Yes? I'm pretty sure it uses a variant of quicksort, but it's completely free to pick the sorting algorithm. The compiler is completely free to pick the sorting algorithm that it finds most suitable. It might even have different implementations for different data types. It could even pick different implementations for arguments of different size or different predicates. So we don't need to know. It's not guaranteed, so the standard says that sort is not guaranteed to be a stable sort, but there is a separate variant called stable sort. So we get that guarantee if we need it. Many more. Position, every, count, remove if, find, merge, map, reverse, concatenate, reduce. This is really the power of higher order functional composition. And the sequence abstraction makes that well, even a little more powerful, because most of these I can use on strings, vectors, and lists without changing anything about how I call them. This is a few more examples of putting keyword parameters together in this space. So member foo in this list I claim is nil. Does that make sense? That must be an error. Or? It's not an error because strings, so well, it depends on how the values, how member compares its values, of course. And we learned last week that the default comparison is EQL, that tests for identity, and two distinct strings can be equivalent but not identical. So this foo here is not the exact same foo as this foo there, in the sense of their memory locations, the actual objects. But I can actually give it a different, I can parameterize member and say use to test hash quote equal a function object, and then this becomes t. So when I give it a test that is applicable to the data type in the collection, then of course there is an equivalent string in the mix. Here I bind that list to parameter foo, and then I sort it using an anonymous function where I say, so the second argument to sort always needs to take two arguments because it's a comparison predicate. So it will compare all pairs of elements from this list. And so here I say determine the length of both of them. So by that it follows they must be sequences. And then say x goes before y, that is return true, if I is less than j, that is x is shorter than y, or in case they have the same length, x compares lexicographically before y. So we've heard about string equal. That's an equivalence test, type specialized for strings. There's also a type specialized comparison operator, less than operator on strings, and that will compare lexicographically. So the result will be increasing length, but where two strings have the same length, they will be sorted as they would be in the phone book. Oh, the phone book, you don't know what that is. You've probably encountered lexicographic sorting. All right, so here again, anonymous function, a function object serves to parameterize the sorting function. What am I doing here? Here I have a collection of pairs effectively, strings and some associated numbers. And I want to sort them by the number in each pair. And to do that, I can say in sorting, apply a function to each element before you compare it. That's the so-called key parameter. So now key is overloaded. The keyword parameter key, that is called key, colon key, is a function object that takes one argument, one element from the collection at a time. It will be invoked on that element. It will return some value, and that value is what will be used by the calling function, in this case sort. So what we get here is we sort by increasing order, so we sort by numeric less than, which we couldn't apply to the lists, to the elements at large. Less than only is well defined on numbers. So colon key, first of rest, so effectively the second element of each element, will bring out these numbers for the sort to compare. So, of course, I can combine various keywords argument. I could, so key, we're saying that down here. So the paradigm, the general idea is parameterization through higher order functions as keyword parameters. And most of the built-in operations, notably the sequence operations that we just introduced, allow colon test, colon key, colon start, colon end. So when I want to count if only in a subsequence, I can say do that from colon start to colon end. I give it some indices and it will only consider the subsequence within these indices. All right, so that was my last attempt at bringing home this notion of the power and flexibility of functional composition, taking advantage of functions as first-class citizens and this notion of higher order functions. That used to be radical 30 years ago. Nowadays even Java has some of this. All right, then let's move on and reflect a little over associative arrays. So now we have sequences broken down into the variable size linked lists and the fixed size integer indexed arrays. Often, of course, we want key value lookup, and you've actually used that in the past exercise already. And hash tables are familiar to you. Lisp has additional built-in associative data structures, and I'll briefly talk about association lists. So an association list, or a list, is a list of pairs where each pair contains a key and a value. So somewhat similar to the last sorting example on the preceding slide. For example, so I can build an association list using the function pairlist. You'd think that must be a typo, or it's, I think, what Seibel would call in a footnote, by historic accident, the T in pair list got lost. So the function really is called pairlist. I couldn't guess why that is. It takes two arguments, a list of keys and a list of values. And so here the keys are keyword symbols, symbols that start with a colon, and hence are self-evaluating, but that's a choice I made. They could be plain symbols, they could be strings, they could be numbers. And it returns a list where each element is a pair containing the first key with the first value, the second key with the second value, and there is a function assoc, and that takes a key and an assoc list, an A list, and returns the entry corresponding to that key, notably the first entry corresponding to that key. So that's like get hash. Only it actually returns the entire bucket, including the key, not just the value. There's a variant of cons, acons, that adds one key value pair to an existing A list. So I extend A list with one more entry, and here it's extended. And in sort of interpreting these, we need to be clear about the funny dot notation here. And that's not necessarily something all of you have seen consciously yet. So far we have constructed lists from cons cells. And there the rest was itself a list. A list, in fact, we defined recursively as either the empty list or a cons cell whose rest is a list. That's the definition of the data type list. But there's nothing to stop me or anyone from giving cons something that is not a list as its second argument. And then effectively what I'm building is a pair, a tuple with two things that are paired, that are tied together. So cons is what we sometimes call universal glue. It ties together two things. When the second thing is a list, then it's convenient to build a recursive list data type, but I can also cons together the symbols A and B. And then what I have is a pair of A and B. And to distinguish that from the list containing A and B, that will be printed with as what is called a dotted pair. So when I see a dot preceding the rest of a cons cell, then that tells me that this is not a proper list. Do you see the difference between what we have there on the slide, which I draw on the board here, the dotted pair containing A dot B, and this structure here, no dot. What is that? That's a list containing A and B. How many cons cells to this list? This is quiz prepping. Yes, 2, 1 per element. The rest of the first is the second. The first of the first is A. The first of the second is B. The rest of the second is nil. We often draw that like this. So this is a list containing A and B. It actually uses 2 cons cells. This is 1 cons cell, where the rest is not a list, but just, in this case, a symbol. So that's what is called a dotted pair, and that's what A-lists use to store the associations of keys with values. And then an A-list trivially uses a list to store the collection. So you might think that doesn't sound very efficient. As with most of the built-in functions, I can parameterize assoc and give it a test to apply in comparing the keys. Here, when I use keyword arguments, keyword symbols, the default test EQL will be fine. In fact, I could even make it EQ. That would be moderately faster, because EQ is really just a pointer comparison. But this means that the keys can be any data type in an assoc list. They can be complete objects. I just need some way of comparing them when I look up an entry. it also means it is actually also the case that I can use an ASOC list for bidirectional lookup. I can look up by the first values, what I called the keys here, but I can also look up by the second value. There's a variant of ASOC called RASOC, reverse ASOC. And that I could use, so I could say RASOC, the string Elvis in a list, and then I would have to say :test hashquote equal. That is, give it a test comparison, a comparison that works on strings. And then it would find that same bucket, and that would be effectively a way of looking up by value to the keys. So reverse lookup. It's not something I can usually do in a hash table. So here we see one benefit of A-lists. Of course, since A-lists use a flat list to record the collection, searching an entry means iterating through the list, scanning through the list until I find a pair that has the right key. That means lookup in an A-list or a P-list, which we don't discuss today, a property list, has worst case complexity linear in the size of the collection and the list length. That is much worse than a hash table. However, this is a very lightweight data structure. Hash tables bring a certain baggage. They're not lightweight data structures. Hash tables need a hash function. They need code to deal with what is called collisions. It's possible that two different keys actually map to the same bucket in the hash table. Hash tables in a garbage collected environment as Lisp may need special code after the garbage collection has run to rehash when the keys may have moved. Then their hash values may actually change. So there's a lot of hidden complexity behind hash tables that we usually don't think about. And hence, for most Lisp compilers that I have used, it's actually the case that an A-list can outperform a hash table on smallish collections. It's more lightweight, it's more nimble. But of course, so smallish collections, in my experience, means hundreds. Once you have more than that, then certainly a hash table is the sort of more powerful data structure, obviously. So then the extra complexity that hides behind the hash table actually pays off. So this may feel out-fashioned, but it actually has some advantages. There are use cases where a hash table is overkill, or there are use cases where you need to look up in both directions, and then if all you have is hash tables, you actually end up duplicating your data because you build two hash tables. One key to value and one value to key. You need not do that in this data type. So hash tables are more efficient for indexing large data sets. Unlike arrays, they are not restricted to numeric keys. They can handle a large arbitrary number of, again, different types of keys. And I need to actually tell the hash table which comparison shall be used on the keys. So I'd say make hash table. And again, give it a :test argument and specify one of the 4 built-in equality tests. EQ, that's the most efficient hash table. That's what I use for symbols. EQL, when the keys can be numbers or characters. Well, EQ I can of course also use with objects that I want to compare by identity. EQL for numbers or characters. Equal for strings or lists. I could use lists as keys and compare them by equivalence. Even equal p, but I'm no fan of equal p, as you know. And then looking up get hash, that's a generalized variable. I can assign it. Nothing new here, really. The one thing I wanted to point out to you is an idiom that tests inserts and updates in a single statement. And that builds on get hash taking a third optional argument, which it will use as the default value in case there's no entry for the key. When I use get hash with a default argument in the scope of an assignment, then the default argument will actually determine what value is assigned. So here I say incf, increment, that is setf, find that thing plus 1. Incf is a macro. We even had the definition on a slide at one point. That will increment in the hash table when there is an entry for the string bar already. When there's no such entry, it will actually create one because the default value for get hash will be returned, incremented, and then that will be assigned to as the new value to the key quote bar, string bar. So that's what we observe here. This is often a very compact way of actually not having to test whether something is there already. So, I mean, typical code, you'll see if get hash something, incf get hash something, else setf get hash something, something. And you can avoid that mouthful by using the third optional parameter to get hash. Right, and of course to iterate over hash tables, we've already seen specialized loop directives for foo being each hash value in hash table. There's also a higher order function called map hash that will take a function argument and invoke that function argument on all values in the hash table. Oh, one more. Actually, I think I'll leave that. For a moment I thought I was through my material, but I think this is the last one. Let me just check that. Yes, okay. So I think we'll take a break here. And then after the break, come back, lecture about one more piece of Lisp, and then have a quiz. So see you in 15 minutes. All right, welcome back. Mohav, I think I counted like 42 or so. How many of you are here for the quiz? Why not be honest? Okay, so 42 is the handover. For the next 6 weeks or so, Mohav will be teaching. I'm sure you will bring that number up to 50. Can be a good idea to wrap up on a quiz, of course. All right, before we quiz, one last piece of relatively boilerplate programming language knowledge. Abstract data types, that is essentially a bundle of data that belongs together. We will, in all simplicity, model using just structures, structs. Lisp actually has an object system, but we're completely ignoring that. So there's something called the Common Lisp Object System, CLOS. You're free to study it. It actually has many redeeming properties, but sort of we focus on the classic part of Lisp. But still, sometimes we need to define a group of data pieces that hang together, and to do that, we'll introduce a structure. There's a special form called def_struct, define structure, and that is nicely integrated with the type system. So even though Lisp is dynamically typed, we don't often talk about types. We don't declare types in our code. Of course, the objects have types. Each object is of a specific type, and hence these structures will also be of a specific type, and they'll essentially serve to encapsulate a group of related data. Something that you could think of corresponds to an object. Every time I use def_struct, I define a new type. I insert a new type into the Common Lisp type hierarchy. And the name of the type will just be the structure name. And the def_struct, as a side effect, gives me the basic building blocks I need to manipulate objects, a constructor, accessors for the individual components, and a predicate to test whether something is actually an object of this type. So I say def_struct album. I say an album comprises two pieces of information, the artist and the title of the album. So these are, in a sense, the names of these properties. Here I specify default values. I wouldn't have had to do that. So they both default to unknown. And then I have a constructor called make-structure name, make album. It takes as many keyword arguments as there are slots in the def struct. And it returns an object that I can bind to foo. This is how Lisp prints them. So again, it looks a bit like a list, but it is not a list. And the initial hash mark tells us that hash s means structure. It's a structure of type album with these two slots, and the artist slot now has as its value Elvis, whereas the title slot has its default value unknown. This object is not a list, but it's an album. So there's the predicate album p, and there are the accessors, structure name dash slot name, album title, and they are generalized variables. I can use them to retrieve from the object or write and assign a new value to that slot. So I can set the title to in the album object foo to blue Hawaii, and now when I inspect it, the title slot has recorded that new value. So that's a lightweight object mechanism. Well, it's not even that. It's a structure. It's a grouping mechanism. That's what we will use to introduce abstract data types that essentially encapsulate groups of related data and obey a standard interface, constructor, accessors, type predicate. Nothing mysterious here, I would like to think. Then, I was going to maybe run a quiz today, but it's really beautiful sun outside. But you're here for the quiz, at least some of you. So Oslo University is a modern, leading international research university. And computer science, of course, is technologically advanced. So we will, this is an exercise in high-tech teaching, really. You'll need a pen, every one of you. This is an individual quiz. And we do this in part to make it even harder for you to fail already on our first obligatory assignment, where there is no second part. And we don't really want people to drop out at this point, unless you realized I can't deal with all the parentheses, or with his voice, or I don't believe in machines learning anything. Then you're welcome to drop out of this point. But through this quiz, you can get up to 4 bonus points. So that's 2/3 of what you actually need to qualify on exercise 1. I mean, we'll really worry if... Actually, the quiz is not that simple. I'll be interested in how many of you actually take home 3 or 4 points. You will submit your answers through a piece of technology called Post-it notes. So everyone will need 1 Post-it. Thank you. And since we're handing out bonus points, we need to identify you. So please write down your first name, your last name. Try your best Sunday school writing. It would be good if we can actually read it. To give us one more cue to your identity, please also write down your UIO account name. Not your Facebook account name, your cat's name. That will not help us. Your account name here at the University of Oslo. That would be OE for me. And then there will be 4 questions, each with a short answer. So at the top of your post-it, who you are. Then 4 lines with your short answers, and prefix each of them with the question number, 1, 2, 3, 4. This is individual, and these points are exam qualifying. So this is my opportunity to lecture you about the rigidity, the strictness of the Norwegian system when it comes to assigning grades and passing exams. We've linked to the relevant piece of national regulations from the course page. And any observed attempt at cheating in exam qualifying situations like this can lead to students being excluded from all Norwegian universities for 1 or 2 semesters. That sounds very harsh. So you talk to your neighbor, you're out. This is, in fact, even more important, and this happens sadly every few years, when you make your submissions to our assignments. So, in earnest now, seriously, when we receive submissions that are not produced individually, that give us the impression of being not the work of your own, the result of your own work, then we are obliged, we are required to look into that. There will often be invitations to meet with us and someone from the study administration, a kind of trial, if you will. This is not fun, but this is how the system works. And then if at the end of the day it's determined you didn't write this, what you submitted, then this actually is passed on from the department to the University Central, and they decide on whether or not you are actually excluded from all Norwegian universities for a semester or 2. It's very draconic. And there's no middle ground. And we have no choice. This is what we are obliged to do when there's any suspicion of cheating in exam qualifying situations. So please, never, ever, even if in the last hour and even if you feel, I really want to go up for this exam, but I just can't work this out just now, copy from someone else or from a source that you don't reveal. That's really not fun and something we would hope to not experience this semester. All right, and the same applies here. Do not consult with your neighbors. There's actually another reason. You know best. So you give your own answers. After the quiz, we'll, time permitting, I think we should have time for that. We need to collect your notes. We give you 2 minutes for each question, so that's a little more than 8 minutes. Put them to the front of your table. These are exam qualifying materials. They will be archived. Honestly. Seriously. You can no longer write on them when we say time's up or after you've started to look at your neighbor's sheet. We'll collect them, and then we'll actually have another round of 4 times 3 minutes or so, where we ask you to form groups of 2 or 3 people and actually discuss your answers and how you arrived at them. And then we will give our answers, and then we can compare notes. So that's a lot of time. That's about half an hour of our time today that we use on this. But in my experience, this sort of talking to your neighbor can often also be a very helpful part of the experience. So please, let's jointly work through this. It requires a little bit of discipline. And of course, the spirit you'll adapt in talking to your neighbor is to explain to them why you're right. And they will take the same spirit. Maybe you agree. And if you don't, that can make for an interesting discussion. Then you try to convince each other of the right solution. Then you reason over the problem even more. All right, any questions? Are you ready? Then, here's our first question. Actually, you didn't say you were ready. So, on the use of const cells, we define 2 variables, give them values, and ask how many const cells are used by each one of them. So 2 numbers for the first question. You don't need to draw them, you just need to tell us the right number. One more minute. Thirty seconds. Time's up. Hands up. Who would have wanted to have more time? 2 minutes was more than you needed. I felt so. Second question. A becomes a value. We define a function foo with a relatively interesting parameter list, not so interesting body, and we call it, and we ask, what is the return value of this function call? One more minute. You got some extra time because my phone alerted me to low battery, and that stops the timer apparently. Who would have wanted more time? Hands up. That's... I'm asking so that you can tell me. All right, our next question. Global and local variables. Foo becomes some value. There's a function by the name foo. It creates some local variables and again returns something that allows us to inspect the effect of all of this trivial computation. And now we call it and compute its arguments and ask, what is the return value of this call? One more minute. Really. Time's up. Who would have liked more time? Couple. Finally, mysterious common Lisp. That's maybe how you sometimes feel at times. Decreasingly so, I hope. So, define question mark, if null, question mark, cons first, question mark, rest, question mark. Remember what we said about the range of valid characters in Lisp symbols. And what argument does question mark take? What argument type? What type of argument does it take? And what does the function compute? One more minute. Okay, so that was it. Before you put down your pens, I would ask you to put 2 more words at the bottom of your page. Hard or difficult, hard or easy, depending on whether you found the questions rather difficult or rather not so difficult. So one of these 2, hard or easy, and slow or fast, depending on whether you felt you should have had more time or no. If you write slow, then you had enough time and maybe more. If you write fast, you would have wanted more time. And then let go of these post-its. We come around to collect them. Please push them pens down, push them to the edge of the table. A bit hard, a bit easy. Both, yeah. We'll ask you more properly 2 weeks from now. Okay, please put these post-its, put your pens down, everyone. We'll collect your answers. Thank you. Thank you. Okay. So if you could form groups of 2 or 3 students, yes. That was smart. Turning it around. Any more post-its to collect? Oh, good. Okay, so that's a large group, but that's all right. You'll surely have the right answer in the pool. So take 2 or 3 minutes, not more, I think, to discuss how you answered this question. Were there different opinions? Try to find out which one is the correct one.
Where do we put the points?
In Devilry. All right. So that's now this is the difficulty in this quiz situation. I want you to discuss and then I want you to listen. Very difficult flow of. So very good discussions, it seemed. I hope you found them productive too. So what's the right answer? How many constants? 5 and 5. You were going to say the same thing. How much disagreement was there in the groups? Some? Some. It's reassuring. So why 5 in both cases? We've said I need 1 const cell for each element in a list. There are 1, 2, 3, 4 elements, and one of them is a list with 1 element. So I need 1 const cell to represent this single list containing 1 element. and that is in the 4th position. It's the first of the 4th cons cell in the top level list. Here I have 2 pairs, dotted pairs. We just talked about them, 1 cons cell each, but one of them again contains the singleton list. So this pair here is 1 cons cell for the list plus 1 for the pair. That's 2 plus 1, 3 for the top level elements, and then there are 2 such elements. So again, I need 2 cons cells for those. That's the reasoning. Nothing mysterious. We'll get to the mysterious common Lisp. Then let's again discuss for 2 minutes on this one. Please. All right. May I interrupt your group internal discussions one more time? So let's jointly discuss. I'll actually, I think, not ask for a suggestion because it's easier to write it down. So this is what I believe the solution should be. In fact, I tested that against the Lisp interpreter last night. So I'm relatively confident of this solution. And here we were playing, well, we were a little creative. We're defining a function that takes one obligatory parameter, followed by 2 optional parameters called B and C, of which the first one has a default value of 42. Any remaining parameters will be bound to, as a list, a parameter that we also call list. And then we give it 1, 2, 3, no, sorry, we give it 1, 2, 3, 4, 5 parameters. But some of these parameters we sort of wrote in a manner that you might feel is an attempt at fooling you. And that's not something we would do in an exam, but in a quiz. No bonus points. No bars held, I think, as they say. So, colon B is a keyword symbol, self-evaluating symbol. It also looks like it could be the way of naming a keyword parameter B if there were such a parameter. But there are no named parameters here. They're optional parameters, but optional parameters are position coded. So this B here, in fact, becomes the value of the second parameter, B, which leaves the next value, 11, for the third parameter, C. Then we do the same thing. Colon rest looks a bit like we're declaring and from here on the rest parameters, but that's not how it works. Any remaining parameters will be collected as the rest list. So remaining starts here, colon rest, and the symbol, so the keyword symbol rest and the symbol list. I need to quote this symbol because it's not a keyword symbol, it's not self-evaluating. I don't need to quote the keyword symbol. And I get the value of A, the value of B, the value of C, the value of list, which is a list containing the two remaining parameters. Did we fool you? Yes. Bonus points should be hard to earn. It's actually a lot easier to earn the points when you submit the. And then we have two more, global and local variables. I still feel we'll do 2 more rounds of group discussions. So please, what's the right answer? What is the return value? Okay. Some groups have brought their discussion to agreement, I hope. So let's jointly give the answer then. Please. So the answer is 2 and 2. You agree? It's not nearly as complicated as it looks. We take advantage of Common Lisp being a Lisp 2 dialect, where a symbol can simultaneously have a value and a function binding. Hence we use def parameter and defun for foo. And then while we're going and having a good time at a quiz, we use the same symbol to name the first parameter to the function foo. That will make it a local variable inside of foo. And then we create another local variable using let inside the body of foo. And another one called bar, which is the same local, it's the same name that we have already used for the first parameter. So there will be several layers of shadowing, of what we call shadowing, of bindings, value bindings for symbols that overlay each other in their scope, in the scope of the let or in the scope of the function body. So first we need to compute before we can call foo, we need to compute its arguments. The first of the rest of foo is the second element. That's 1. The first of the last of foo, need to remember that last returns the last non-nil cons cell, or the last cons cell. So the last non-nil rest in a list, and hence taking out the first is the last of the last is the last element. That's 2. So we call foo with 1 and 2. That means this foo 1, this bar 1. Now we establish a new binding for foo. This is still the parameter foo because the new binding is not in effect yet. So 1 times 2, that's 2. So this foo, the local value variable inside of the let, will be 2. And bar we compute as foo plus 1, the new bar, the innermost bar. And the let, we said in passing, establishes all of these bindings in parallel. So this foo here is still this foo. It's not yet this foo. That would be different in a let star. The let star is the sequential variant. There, this clause would already see the effect of this clause. Not so in let. So this foo is still this foo, which was 1, I think. So 1 plus 1 is 2. Foo bar. That gives us the right result. All right, one more. Finally, we'll demystify Common Lisp. What argument type does it take, and what is it that the function computes? 2 minutes. All right. Can I, for the last time today, interrupt your group internal deliberations and wrap up this lecture in a kind of controlled manner as good as I can in the remaining 3 minutes? Please. Shh. All right, what argument type does it take? We can answer that kind of question by looking at the kind of functions we invoke. Again, question mark is just a symbol, and we use it as a function name and as a parameter name. Really nothing mysterious about that. And we call first and rest and null on it, so what kind of object? That's a list. And what does it compute? That's slightly more intricate to answer. When it's given the empty list, it returns the empty list. When it's given something that is not the empty list, it returns a fresh const cell containing the first element and calls itself recursively over the rest. That means for each const cell in the list, it will create a new const cell whose first is exactly what was the first in the original, and whose rest will be the result of calling the function on the rest. So what the function does is it creates an equivalent copy. All the same values, but wholly new const cells. All right. I have one slide on good Lisp style. I think I'll actually skip over that. Some style recommendations. Please maybe look at them. Elena may actually comment on how you format your code, because it really makes a difference for us, also for you. So indent properly, don't put closing parens on a line by themselves. We're not writing block structured C++ or Java. Use Emacs and auto indentation. Make your code look pretty. It makes it easier for Elena to grade and Mohave to grade pretty soon, probably, when assignments get more complicated. And a happy grader means it's in your own best interest. Finally, next time we'll shift gears. We're done with the introduction of programming language with interesting properties and some historic significance, which we will now turn to use in machine learning techniques applied to natural language. And next week we start talking about distributional semantics, so-called vector space models for the meaning of words. Thank you for today. See you next time. I need to stop the recording.